Welcome back to Maths with Mrs. J. This is going to be my final video in my short series about index laws. In this video, I wanted to combine a little bit of our knowledge about our index laws and writing bases as powers of primes and use that to simplify some expressions. If we're having a look at our first example here, I want to simplify 8 to the k times 2 to the k. Well, we want to write both terms with the same base. 8 is 2 cubed. You can put brackets and then the k, but it's pretty obvious that we're going to be multiplying the 3 and the k anyway. So when we put them together, they're 2 powers with the same base and we're multiplying, so we're going to add those indices. This one here, we want to write everything with the same base if possible, or at least powers of primes. In this case, it is possible to write everything as base 5. So this is going to be 5 squared to the t, which is 5 to the 2t. This is going to be 5 cubed, all raised to the t minus 1. Let's just tidy that up a bit. So in the numerator, we're going to get 5 to the 3t. In the denominator, we're going to get 5 to the 3t minus 3. Now, the numerator power is greater than the denominator power. And when we subtract them, 3t, let's just do it up here, 3t minus 3t minus 3 is just going to give you 3. So you're going to get 5 cubed, and you can put that as 125 if you like, or you can leave it as 5 cubed. This one here, we can write everything with base 2. That's obviously 2 to the 4th. 4 is 2 squared, so we're going to get 2 squared squared. 2 to the 4th by 2 to the 4th by 2 cubed. We're just going to add all those indices and get 2 to the 11. This one here, let's see how we go. We can actually write all of those in base 3. So 27 is 3 cubed, 81 is 3 to the 4th, 9 is 3 squared, and 3 is obviously just 3. Using our index laws, we get 3 to the 6th times 3 to the 4th on 3 to the 6th times 3 to the 5th. Well, they cancel out completely. This is the bigger power. We're going to be left with 3 to the 1 in the denominator. This one here is a little bit harder because we have different bases involved. 35 is 5 by 7. 5 is obviously 5 and 7 is obviously 7. 25 is 5 squared and 49 is 7 squared. So here we're obviously working with bases 5 and 7. So we're going to get 5 squared by 7 squared by 5 squared by 7 to the 6th over 5 to the 8 by 7 to the 6th. Tidying up the numerator, we get 5 to the 4th by 7 to the 8th, denominator 5 to the 8th by 7 to the 6th. The bigger power of 7 is in the numerator, so we're going to do 7 to the 8th divided by 7 to the 6th is 7 squared. The bigger power of 5 is in the denominator, so we're going to do 8 minus 4. I'd be inclined to probably just leave it like that. You can, if you want to, do your 49 over your, 625 or whatever. But it's okay to leave it like that. Question 6 is a little bit of an interesting one. The reason why I picked this is that it is a little bit different. We've got a plus here. But let's think about what we know about our index laws, and let's think about some way that maybe we might be able to cancel. If we want to cancel, we want to have a product over a product. How do we get that? By factorising. What is the lower power of 3 in our numerator. It will be 3 to the n, won't it? What do I multiply that by to get back where I started? I'd need a 1 and I'd need a 3 to the 1, wouldn't I? Because 3 to the n times 1 is 3 to the n. 3 to the n times 3 to the 1 is 3 to the n plus 1. In the denominator, the smaller power is 3 to the n minus 1. To make that work, I'd have to multiply it by 3 to the 1 plus 1. Now, we're quite lucky here that those brackets completely cancel out. They're both just 4s. And then to work out what we've got left, we're really doing n minus 1, which is n minus n plus 1. So we just get 3 to the 1, which is 3.